Hey, what's up, super peeps? Just looked outside and it's snowing. Woohoo! Anyways, so today we are going to continue on with bonding. So we dealt with some ionic stuff yesterday. Today we're going to deal with some covalent bonds. So our covalent bonds usually form between two nonmetals. And we also find them in the polyatomic ions. So this is when electrons are shared between two atoms. Now, they're still trying to get that octet. Except for those few that only want two. All right, so they're sharing these electrons to create that full octet of electrons. They want to fill those s and p orbitals. All right, now, there are two types of covalent bonds. If the electrons are shared equally, this is a non-polar covalent bond. And if you remember from yesterday, the electronegativity difference is from 0 to 0.4. So if we're between 0 and 0.4, the electrons are shared equally between the two atoms, and it is a non-polar covalent bond. Okay. The second type of covalent bond are where the electrons are shared unequally. In other words, they're pulled towards one of the atoms. And our electronegativity difference from this is above 0.4 all the way up to, let's say, 1.9. Remember, we said that there are some issues up here at the top, but let's say 1.9. So here the electrons are shared unequally, and these are called polar covalent bonds. Right? So these are going to have oppositely charged ends. Okay. So we need to spend some time figuring out how to draw the Lewis dot diagrams of covalent conjugates. Remember, these are also called dot diagrams. So this is how I want you to kind of do it, right? So step one is just to add up all the valence electrons of each element. Second step. Figure out which element is the central atom. Now, there's two things that you should be able to do here. Right? First of all, usually the least electronegative atom is the center atom. So usually the one that has the lowest electronegativity value is the central atom. But really, you're just going to use common sense. Okay, use common sense. So for example, if I have H2O, okay, either one of the hydrogens or one of the oxygens has to be in the middle. All right. So in this case, we only have one oxygen. So the hydrogens are probably on each side. So my oxygen would be my central atom. All right. That's what I mean by use common sense. How about this one? Let's say we have CCl4. Okay, and I have to figure out my central atom. Well, do you think it's one of the chlorine atoms or the carbon atom? Well, common sense is going to tell me that the carbon atom is going to be in the middle and the chlorines are going to be around it. Okay. Ammonia, same idea. What's going to be in the middle? Nitrogen. So you can use common sense really to figure out which of those atoms is going to be in the middle. Our third step is to draw a skeleton structure. And I'll show you what I mean by that. Step 4. Fill in electrons to complete the octet rule around each atom. Now remember, some elements only want 2 electrons. Okay, and we talked about those yesterday. Step 5. If you do not have enough valence electrons to make complete octets, there must be a double or triple bond. All right, so I'm not sure how you were taught to draw these Lewis dot diagrams, okay? And I taught my honors kids a little bit different than this, but it's kind of similar, all right? So let's just go ahead and do it a couple times, a bunch of times. So let's start with, I don't know, how about CH4? So our first step is to just figure out how many valence electrons we have. Well, carbon has 4 valence electrons. Okay, each hydrogen has 1, so the hydrogens also have a total of 4. So that means I have 8 valence electrons to play with. That's it. Okay, I can't use any more, I can't use any less. That's it. Right. So now, the next thing I'm going to figure out is, I want to figure out what my central atom is. Well, again, this is common sense. Okay, I got 1 carbon and 4 hydrogens. Probably the carbon's going to be in the middle. And the hydrogens are going to go around it. Now, when we're placing things around things, usually it's top, bottom, left, right. Top, bottom, left, right. Okay, you don't go off the corners. Well, in some cases you do, but all right, generally we're top, bottom, left, right. So I have 4 hydrogens, so I'm going to put 1 on the top, 1 on the side, 1 on the side, 1 on the bottom. All right, so this is what's called my skeleton. Got my central atom, and I got my hydrogens around it. Now what it's telling me is I have to make a bond here, I have to make a bond here, I have to make a bond here, and I have to make a bond here. Right, and I have 8 valence electrons. Now remember, hydrogen is one that only wants 2. Okay, so it's going to share a pair between carbon and hydrogen. It's going to share a pair between carbon and hydrogen. Same thing here. And same thing here. So I have 1, 2, 3, 4, 5, 6, 7, 8. So there are my 8 valence electrons. Now, my carbon atom, it wants 8, so it has 8. And it does have 8 valence electrons. The hydrogen only wants 2, and it has its 2 valence electrons. Right? So each one of these follows that octet rule or the duet rule, all right? And everyone's happy. Now, this is called the Lewis diagram. Let's see if we can name this bond. Right, so we have 2 nonmetals. It's a covalent bond. Okay, so let's name the specific bond. Well, we're sharing 1 pair of electrons. If we have 1 pair of electrons, that tells us that it is a single bond. Now, the question, are these electrons being shared equally or unequally? Now, if we look up electronegativity values, carbon is 2.6. Hydrogen is a problem. Depending where you look, hydrogen is either going to be 2.1 or 2.2. All right, and it's the discrepancy is really between, it's like reality, it's 1.4999 or something like that. All right, so depending who you talk to or where you look, it's either 2.1 or 2.2, which makes a really kind of a difference here. In our textbook, it's 2.1, but I'm going to tell you to use 2.2, and here's why. When we actually do some analysis of the bond between carbon and hydrogen, these electrons are shared equally between the carbon and hydrogen. They aren't pulled one way or another, all right? Which means this is a single non-polar bond. And if I do this difference here, I get 0.4. If it's a 2.1, I get 0.5, and that might tell us or indicate that it's a polar bond. It's not. Okay, so use 2.2 if you have to use that difference for hydrogen. Now, so let's finish this up. This would be a single because it's sharing 1 pair of electrons, non-polar because the electrons are shared equally, covalent because the electrons are shared, bond, all right, which is a force of attraction between 2 atoms. Okay, so let's kind of go through this name again. Okay. Bond. A bond tells us that there's a force of attraction between 2 atoms. The covalent part of the name tells me that the electrons are shared. The nonpolar part tells me that they're being shared equally. The single part tells me that I have 1 pair of electrons being shared equally, okay, between those 2 atoms. Now, how many different bonds do I have? Well, this is another bond, this is another bond, and this is another bond. They're all the same bond. So in this case, I would have 4 single, nonpolar, covalent bonds. Now, while we're here, let's do this. So this is called the Lewis diagram. From the Lewis diagram, I can get the structural formula. And our structural formulas tend to show shape. Okay, so this is going to be a tetrahedral, and we're going to talk about those. But instead of dots, we're going to use dashes. Okay. For now, this would be fine. Eventually, okay, it won't, because this really is not how we draw a tetrahedral. For those of you that remember, a tetrahedral structural formula looks like this. This dotted line means the hydrogen is coming out of the paper, or it's going into the paper. Right? So we'll deal more with shape All right, but you can actually, you're going to draw your Lewis diagrams, and then eventually we'll use those diagrams to turn them into structural formulas. All right, so this is methane. Let's try another one. Let's try H2O. First thing we're going to do is we're going to count up our valence electrons. Oxygen has 6. Each hydrogen has 1, so the hydrogens have 2. So that means I have 8 valence electrons to play with. Right? Again, I'm going to make a skeleton. What's going to go in the middle? Well, oxygen's going to go in the middle, just by common sense. And our hydrogens are going to go on the outside. Now, I'm going to do this. I didn't have to do this. It could have been up here. It could have been over here also, all right? But I'm going to put it this way, right? Which is telling me I'm going to form a bond here, and I'm going to form a bond here. There is no bond between the hydrogen atoms. Right? So now I have 8 valence electrons to place around here. Right? I know hydrogen can only make 2, so I'm going to put those there. I'm going to put those there. I have 4 left. Okay, let's go ahead and count. Remember, oxygen wants 8, so it has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has its 8. He's happy. This hydrogen wants 2. He's got his 2. And this one wants 2. So everyone meets the rules for the octet. Right? All right. So now let's go ahead and look at this bond. Well, we know that it is a single bond because we have 1 pair of electrons being shared. All right. Are these electrons shared equally or unequally? Well, if we look at the electronegativities, oxygen we can look up is 3.4. Hydrogen is 2.2. So we end up with 1.2 difference, which tells me this is polar. The electrons are going to be pulled towards the oxygen. They're pulled towards the one that's more electronegative. So they're going to be pulled up here towards oxygen. So this would be a single polar covalent bond. Bond, force of attraction between 2 atoms. Covalent, electrons are shared. Polar, the electrons are shared unequally. They're pulled here toward oxygen. And single tells me that we have 2 electrons or 1 pair of electrons being shared. Okay. The structural formula of this is actually a bent molecule. So it would look something like this. And we'll talk more about shape and structural formulas later. All right, but what I want you to realize is that this 1 pair of electrons turns into 1 dash. All right, let's try another one. Let's do a polyatomic ion. Let's do the ammonium ion. Okay, this charge matters. So we're going to do our normal thing with counting up valence electrons. So nitrogen has 5. There are 4 hydrogen atoms. Each one has 1, so this would have 4. If we add those up, it's a total of 9. But this plus sign means that we have lost 1 electron. So we have to subtract 1 electron. So we only have 8 electrons to play with. We only have 8 electrons to play with. All right, so let's go ahead and draw this. Our central atom is going to be nitrogen. We'll have hydrogen, and hydrogen, hydrogen, and hydrogen. Remember, hydrogen only wants 2. Okay, so this is another one that's pretty simple. He wants to, he wants to, he wants to, he wants to. Now we can go back and we can count. This hydrogen is good, this hydrogen is good, he has 2, he has 2, he has 2. Our nitrogen wants 8. He has 8. Okay, so everyone's happy there. Now, this is an ion. It's going to go in brackets. And it has a +1 charge. Okay, so this would be the ammonium ion. Now, let's go ahead and name these bonds. Okay, now they're all the same. Okay, but let's name this bond right here. Well, we're sharing one pair of electrons, so that's a single bond. Okay, how are they shared? Well, to do that, we're going to look at nitrogen. We're going to look at hydrogen. If we look up nitrogen's electronegativity value, it's 3.0. Hydrogen is 2.2, so we get 0.8. That tells us that they're shared unequally. They're going to be pulled towards nitrogen. So this is a single, polar, covalent bond. Okay, let's try diatomic nitrogen, N2. We're going to do it the same way. So we know that nitrogen has 5 valence electrons. We have 2 nitrogens, so we're going to have 10 valence electrons to play with. Now, there's only 2 atoms, so there's no central atom. They're just going to be next to each other. Okay. And now I have 10 electrons to play with. So I'm going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't put any more. I only have 10 valence electrons to play with. That's it. Okay? There are no more. Now let's look. So nitrogen wants 8 valence electrons. This one has 8, but this one only has 4. Okay? This is incorrect. Okay? We don't have enough electrons to complete the octet around nitrogen. What that's telling me is there's a multiple bond. In other words, a double or triple. Okay, there's a double or triple bond between here. Well, the question is, okay, is it a double or is it a triple? And sometimes this will help. If we draw the original dot diagrams of each one of these, we can kind of see what's going to happen, because what we're really doing is we're pairing up electrons, right? So if we look here, this guy needs 3 electrons, this guy needs 3 electrons. And what ends up happening is these guys pair, and these guys pair. So we're pairing up, or we're making 3 pairs of electrons between the 2 atoms. So let's redraw this. If I make this a triple bond, okay, so that's 1, 2, 3, 4, 5, 6. I have 4 more electrons. Let's put 2 here, and let's put 2 here. The question is, does this follow the octet? Does this follow the octet? Well, let's look at this guy. How many does he have? 1, 2, 3, 4, 5, 6, 7, 8. He's good. Now let's look at this guy. 1, 2, 3, 4, 6, 7, 8. Each of them have their 8 valence electrons. So let's go ahead and look at this bond. We're sharing 3 pairs of electrons. That's not a single bond. This would be a triple bond. All right, so let's name it. So we would have a triple. Now, are these electrons being shared equally or unequally? Well, they're the same element. If we do an electronegativity difference, nitrogen is 3.0 minus 3.0, it tells us that it's 0, which is telling me that it's nonpolar. Right? But if it's the same atom, it's gonna be, these electrons are gonna be shared equally. So this would be a triple, nonpolar, covalent bond. All right. Let's try another one. Let's look at diatomic oxygen. Actually, before that, let's look at, I want to go back to this for 1 second. Notice how I put this unshared pair on the outside. The unshared pairs want to be as far away from this triple bond as possible. So if I had put it up here, it wouldn't technically be wrong, but it's kind of like bad English, all right? It would be like slang, all right? So it's not really wrong, but it's not right either. So we tend to put the unshared pairs far away from each other and other bonds as possible, which is why this goes over here. And I say that because we have a similar issue with diatomic oxygen. So the first thing we have to do is figure out number of valence electrons. Okay. Oxygen usually has 6. We have 2 of them. So we have 12 valence electrons to place. Okay. I'm going to put 2 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, this guy is missing 2 electrons. I don't have enough electrons to draw this structure this way, which means this one also must have a multiple bond. So how the heck do we figure out if it's a double or triple? Well, you can just do it by trial and error. All right, so let's say this is a triple. 1, 2, 3, 4, 5, 6. Then we got 7, 8, 9, 10, 11, 12. Okay. Well, first of all, this is incorrect. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, this isn't correct because now this guy has 6, 7, 8, 10 electrons around it. So that can't be right. If I put this guy over here, again, that's the same thing, just reversed, so that's not correct. So this can't be a triple bond. All right, can it be a double bond? Okay, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. Now, does everyone have 8 valence electrons? Now, let's count oxygen first. It's got 1, 2, 3, 4, 5, 6, 7, 8. He's good. Let's count this one. He has 1, 2, 3, 4, 5, 6, 7. He's got 8. So everyone follows the octet. Okay. So this is a good structure. Right. Now, let's look at this bond right here. So we're sharing 2 pairs of electrons. So this would be a double. nonpolar covalent bond. Now, again, let me just show you something real quick, because I think it's easy to see it this way. If we draw our original dot diagrams, you can see what's going to share, all right? So this electron right here wants to share with an electron over here, so it's going to share with that one. And then this one's going to share with this one, so I'll have two pairs of electrons sharing. So you can kind of do it by trial and error to figure out what it is, but you can look at the dot diagram and figure it out also. Okay, so there's kind of a couple ways to do it. All right, let's get into a little bit more complicated one. Let's look at C2H4. Here's a hint. If you have carbon, it will always somehow be in the middle. Okay? Hydrogen will never be in the middle. It only makes one bond. All right, so it'll never be in the middle. Carbon makes up to 4 bonds. Okay, so it'll always be somehow in the middle. Okay, so let's figure out our valence electrons. So carbon normally has 4. Okay, there's 2 of them, so that's 8. Hydrogen usually has 1. There are 4 of them, so that's 4. So we're going to have 12 valence electrons to play with here, and that's it. All right, well, what are we going to do here? Carbon has to be on the inside of the molecule, so I'm going to put that here first. I'm going to put them on next to each other. Now I have 4 hydrogens. Would it make sense to put 3 of them on this one and 1 of them on that one? Probably not. All right, so we're going to go ahead and we're going to put 2 of them on each carbon. This would be my skeleton. Now, what is this telling me? Well, it's telling me there's a bond between these 2 carbons. There's a bond between this carbon and this hydrogen, this carbon and this hydrogen, this one and this one. There are no bonds between the hydrogen atoms. Now, I have to fill in my 12 electrons so that this fits. So I'm going to start by doing my hydrogens, because I know this one's going to have 2, and this one's going to have 2, and this one's going to have 2, and this one's going to have 2. So that's 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12. Let's just say that. Is this okay? Well, it's not, okay, because this carbon only has 6 valence electrons. It wants 8, so this structure isn't right. This is telling me that I must have a multiple bond. I can't have a multiple bond here between carbon and hydrogen. Hydrogen only makes single bonds. So that means this has to be a double or triple bond. So let's redraw this. I'm going to put my singles in again. This time, I'm going to make this a double bond. So now I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used my 12 valence electrons. If I go back here and count, hydrogen has 2, hydrogen has 2, hydrogen has 2, hydrogen has 2. Each one of those is good. If I look at this carbon atom right here, it has 1, 2, 3, 4, 5, 6, 7, 8. This one has 1, 2, 3, 4, 5, 6, 7, 8. Right? So this follows our octet rule. Right? Now, I want to show you something. Okay. Up here, when we did oxygen, okay, we put these unshared pairs off the corners. Right? So these unshared pairs, they repel from each other and from this double bond. So instead of putting them top and bottom, we put them on the corners. Well, this is doing the same thing. Okay. These three bonds want to be as far away from each other as they can. So what ends up happening is we end up getting something like this. They go off the corners. If you did it like this, I would not take points off, but this would be a better drawing. Okay, this would be a better structural formula. All right, now, let's go ahead and name some bonds. Okay, so let's start with, we have 1, 2, 3, 4, 5. There are five bonds here. 4 of them are all the same. So this is a carbon-hydrogen bond, carbon-hydrogen bond, carbon-hydrogen bond, carbon-hydrogen bond. This bond type of bond we've already named. Single, non-polar, covalent bond. Let's name this one. Well, we're sharing 2 pairs, so this would be a double. Okay, it's the same element, so the electrons are going to be shared equally. So that means it's non-polar. They're shared, covalent bond. Good. Let's try one more. What's CH3F? All right. Let's figure out how many electrons we have to play with. Carbon has 4. These hydrogens each have 1, so that's 3 more. And fluorine has 7. So we have 14 valence electrons. 14 valence electrons. Okay. What's going to go in the middle? Well, if you have carbon, it goes in the middle. Now I have 4 things to put around it. Now, I did not have to put the F here. It could have been here. It could have been here. It could have been here. It does not matter. Right? Let's go ahead and start placing electrons. We have 14 of them to play with. I know this hydrogen needs 2. This hydrogen needs 2. This hydrogen needs 2. So I'm going to put those in automatically. So that's 1, 2, 3, 4, 5, 6 we've placed already. Carbon, I'm going to make this bond a single bond because that would give it carbon 8. So now I've used 8 electrons. I have 6 more. 1, 2, 3, 4, 5, 6. So fluorine has its 8 valence electrons. Carbon has its 8 electrons. Hydrogen each has its 2. So this follows the octet rule. All right. Let's figure out bonds. So we've already named this one multiple times. So let's just name this bond right here. Well, it's a single bond because we got 1 pair of electrons. Is this polar or non-polar? Is it pulled one way or another? Well, if we look at fluorine is 4.0, carbon is 2.6, so that's 1.4, right? Which makes it polar. The electrons are going to be pulled towards fluorine. Okay, so this is a single polar covalent bond. Now, I want to show you something with carbon. So if we look at their individual dot diagrams, that's carbon. Come on. Fluorine, hydrogen. So it doesn't look like carbon can make 4 bonds. Okay, so this guy right here, okay, is already paired. This guy looks like it's only going to make 2 bonds. Fluorine wants to make 1 bond because it has this 1 lone electron. Hydrogen wants to make one bond because of one lone electron. So how the heck does carbon make 4 bonds? Well, it does something funky, and we'll talk more about it later on. It actually doesn't act like this. These 2 electrons for carbon always split. And carbon acts like that. Okay? It acts like it wants to make 4 bonds. So these 2 electrons split. Okay? We'll talk about why later, just not yet. Right? They split to make these 4 bonds. That's why this happens. Okay. Now, I just want to show you one more thing that I make my honors kids do, and you'll see it. All right. So in our dot diagram, sometimes we like to show the polarity. Okay. So this is the dot diagram for hydrogen. This guy right here, these 2 electrons are shared equally. And to show that, I have my students draw circles. And around these, the circles would be the same size. Which is telling me, so this is kind of like a Venn diagram, it's telling me that the electrons are shared equally. Now let's say that I have something like HF. So fluorine is 4.0 minus 2.2, it's 1.8. Okay, this is very, very polar. So these 2 electrons are pulled over here towards fluorine. And what I do, like I said, okay, is we draw a Venn diagram kind of, and I make this a really big circle. Big circle, big. Look at the little tiny circle over here, this small little circle. And what I'm trying to show is that these 2 electrons that are being shared are pulled towards the fluorine. Right? That's what these different size circles are really telling me. So if you have the same size circle, okay, they're equally shared. And if you have one circle that's bigger than the other, the big circle is around the electron where the electrons are pulled towards. All right? It just visually shows you what's going on with these shared electrons. Right? Okay. Unfortunately, there are lots of exceptions to the octet rules. We're going to kind of work our way through some of them. First of all, Lewis structures of odd valence electrons, electron compounds. Okay, this is going to probably be an exception. So if the total number of valence electrons in a molecule is odd, it is impossible to construct a Lewis structure that follows the octet rule. So for example, NO2, okay, nitrogen dioxide. This is actually very, very unstable molecule, right? But it will form. Okay, so if we figure out valence electrons, right, it turns out this has 17 valence electrons. It has an odd number. Well, let's see if we can draw our Lewis structure. Nitrogen is going to go in the middle, and our oxygens are going to be around it. Question is, what type of bonds am I going to get here? And I'm going to do this just to see what's going on here. So nitrogen looks like this. It looks like it's going to make 3 bonds. Oxygen is this. It looks like it's going to make 2 bonds. So what's going to happen here? Well, what am I going to do? Well, I'm going to pair up this guy with this guy, this guy with this guy. These aren't going to split, so they're going to stay by themselves. So that means this is a double bond. That's going to pair. This is a problem, because usually those aren't going to go together. But I'm going to put him with him, so this is going to be a double bond. So now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Everyone's happy. Everyone has 8 valence electrons. How many total valence electrons did we use, though? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Look here. We have to use 17. We didn't use this 1 electron. Okay. So where does that 1 electron go? Well, here's the rule of thumb. The least electronegative atom will be the one that does not follow the octet rule. So this electron would sit right there. Now, the reason I know that nitrogen is 3.0, oxygen is 3.6. Okay, so this nitrogen would have an extra electron, and we'll talk about how that happens in a little bit. All right, nitrogen, this does not, with nitrogen, it almost never does this. This is one of the very few exceptions that nitrogen does not follow the octet rule. Okay, almost always does. All right, but this is one exception. Now, this is very unstable. It's very unstable. Okay. It's got this unpaired electron sitting here. Right? That gives it a lot of potential energy. So molecules that have unpaired electrons are called free radicals. They're called free radicals. Now, hopefully in your bio class, you talked about free radicals. Free radicals, these are things, and you maybe just in life have heard about them now. In our bodies, okay, free radicals form, and we don't want them in our bodies because they're very unstable and they're going to bond with something else. And it could be something in our body that we need. It could disrupt our DNA. Okay? If we disrupt our DNA, all right, it's going to cause a mutation, which could lead to cancer. All right, so free radicals in our body are a bad thing, but really what they are molecules that have an unpaired electron, just like this one. Okay. Now, free radicals, okay, will often combine to form what are called dimers. So for example, two NO2 molecules will come together to form N2O4. And it would look something like this. Okay, the one unpaired electron from each one are going to pair up. And this is what would be called a dimer. And again, nitrogen's not following the octet rule, all right, but this does form. All right, so I think that's where we're going to stop for today. All right, next time we will continue on with our list of atoms and things that don't follow the octet rule, and we'll get into resonance. All right, so have an excellent day.